This is the lab.
Okay. There we go. Yeah, I don't think there was too much to turn in really, but. All right, thank you. So, yeah, so let's talk about a few things. Let's see, today's the 20. Yeah, so I think the next lab won't be next week, but it'll be the following week, which I think is the week of, first week of October. What's that, the 5th and 6th or something of October? I think it's, yeah, 5 and 6 October. That Monday and Tuesday. Just so we'll have the same lab sections like we did before, where there's a morning, I think from 9 to 11, right? And then there's one in the afternoon from 2 to 4 or something like that. So again, so you'll keep the same lab sections. And then the other thing I wanted to do was for the midterm exam, I was thinking either the Tuesday, the 20th of October, or the Thursday the 22nd of October. So I'm fine with either of those, depending on, do any of you have preference? Like you don't want it on one day versus the other?
We would be doing it in class either day, correct?
What?
Would it be in class
Sure.
either? Okay.
Yeah.
22nd.
The 22nd?
The OSA conference is the weekend before that, so.
What? Oh,
The OSA conference.
Yeah. So it's the week after that conference, right?
Yeah, so as long as, Tuesday's fine, but Thursday.
Yeah, Thursday's fine. We could do Thursday. And then I can grade them over the weekend and get them back. So, all right, so let's have the midterm on that. And I will, I'll post like last year's midterm so we can have a look at the types of questions I ask. And then on the 20th, I will review the previous year's midterm, so you have an idea of how to solve those problems and so forth. So just to to kind of let you know, and then I posted some new lecture notes on the D2L site, so you can go up and check those out. Like I noticed that the stuff I will be talking about today wasn't quite up there yet, so I put that up there, which is always good. Unfortunately, it's not typed yet, but hopefully it's legible. So I'll do the best I can, and I'm going to go over it here again. And then there's several others. So today I figured we're going to do the lens, the Fourier transforming aspects of the lens. We're then going to look at sort of a Fourier analysis of an off-axis hologram situation to see how to set up or design the hologram and what conditions are necessary to get a kind of an unbiased reconstruction from that hologram. And then the third thing that we'll look at are some of the holographic geometries. So I put up some of those notes for you, so you should have them now. All right. Okay. So any questions on any stuff going on? And then we have homework 2, which is due sometime, either
I think it's next Tuesday.
I think it is next Tuesday. Yeah. So that would be like the 29th or something. Yeah. So homework 2 is due 29, not October, September, Tuesday. Okay, very good. All right, so we've been spending the last couple of lectures looking at some Fourier analysis of different apertures and gratings and so forth. And, we found that we can really come up with some nice descriptions if we go into the far field. However, we need, kind of a long distance. We need to have z much greater than something that looks like this, where this might be the size of the aperture that we have. And because, the wavelength is, in microns, even if we had millimeters here for these dimensions, we end up getting into dimensions that are, hundreds of meters and even a kilometer in length, which is, kind of big for an optics lab. So we can greatly reduce this down to the dimensions of lenses, basically, by using a lens in the system. And then towards the end of the lecture today, I think I'll get to talking about the Fourier transform holograms, which use the lens in one way or another. So we'll look at two cases here. So we have case one, where we have the lens in our system. Of course, the lens is characterized by an aperture and a diameter and a focal length. And so in this first case, what we'll do is we'll put the object transparency. So we have this object transparency. We'll put it right next to the lens, and then we illuminate it with a normally incident plane wave. If we come in with an off-axis plane wave, and we'll get to an example of that later when we do the Fourier transform hologram, we'll end up, we'll shift this point off-axis, right? So we can illuminate it with other types of waves. We can use a spherical wave. We can use a pre-aberrated wave. So we can modify this in a number of different ways. But for now, we'll keep it simple and just have a normally incident plane wave illumination on that. All right, so this will be the first case that we'll look at. And in this, so what we have to do is, what we want to do is look at what happens again in the back focal plane of this lens. All right. All right, so the first thing we have to do though is, we know like what the transmittance function, if we have a transmittance function here, say t sub a of x and y or what have you in this incident plane for the transmittance function, we know that we can then just take the Fourier transform of that in the far field to come up with the diffraction pattern. However, how do we model this lens incorporated in this? And so we can model the lens by having a transmittance function for the lens. All right. So the question now is, what is the transmittance function for the lens? All right. Well, if we look at just a basic kind of spherical, let's say a biconvex spherical lens, and we can modify this, of course, we can think of it as having 3 parts. All right. So here's our lens here, and so we have basically 3 parts that we can identify. One is a portion of the lens to the left, say, of the bisector. It may have a center thickness here, which is delta 0,1, and it has a radius of curvature. We'll use the convention that when the curvature is to the left of the rotation point here, it's a positive radius. All right, and so that's one component. All right, and then of course we have another component. So we have also we can have a second sort of section that looks like this, a plano-convex section out here, and this one has a different, say, can have a different center thickness. It could have a different radius of curvature, and so this radius of curvature here, if we draw it this way, this is going to be a negative number. All right, so again, the rotation is to the right of this vertex here. Okay, so and then we can make this, say, a thick lens. And so we can possibly, I'll draw it outside here, but we can have another section here with, say, a slab, planar slab here with thickness delta 0, 2. All right, so that's our thickness at the center there. These are kind of the thickness along the axis here and there. All right, so how do we make a transmittance function from that? All right, well, we could look at the, yeah.
Is the slab the center of the lens that we're just taking out, or is it?
This should go in there. Okay, so we put these three guys together. Yeah, like that. So I didn't mean to confuse you on that. So this is the 1, the 2, and the 3, although I'm going to use R2 for the second radius of curvature since there's only 2 radii of curvature there. Okay. So this is what we have broken down. And of course, here we have, we're going to have some index in each of these glass sections as we look at that, all right? So if we just look at the thickness functions, then for this lens, for this one, so this is our delta 1 here, and this is delta 3, which will be a function of x and y, and that will be a function of x and y. This one will not. This one will just be constant, all right? So we'll see how that factors in a little bit later. So if we look at simply these various thickness functions, what we have for this section here is we have, say, delta 1 of xy is going to be equal to that center thickness, delta 0, 1, minus the thickness associated with this planospherical section, which is r1 minus the square root of r1 squared minus x squared minus y squared. Okay? And so we'll let's write that more suggestively here as how we're going to solve this. So we could factor out an r1, and this becomes 1 minus the square root of 1 minus x squared plus y squared over r1 squared. Okay? And then similarly for section 3, the thickness function delta 3 of xy is equal to delta of 0, 3 minus a minus r2. Remember, this is a negative, and we're talking about a thickness here. So we have a minus r2 minus, so this, again, just to write this out, this is a positive number. Here, minus the square root of r2 squared minus x squared minus y squared as above, and so that's equal to delta O3 plus, okay, again, because of this notation that we have here, r2 times 1 minus the square root of 1 minus x squared plus y squared over r2 squared. Okay. And also, if we look along the axis, so along the axis, the optical axis, we have, delta, basically, we could call that delta 0 for the total kind of thickness here. That's going to be equal to delta 0, 1 plus delta 0, 2 plus delta 0, 3. Okay, so we're trying to construct, again, a phase function from this. And so as you might kind of guess here, we need to get rid of those radicals to put this in an exponential and play with it. All right, so we'll use our old friend, the binomial. Yeah.
Would it be +1 plus the square root of 1 minus for the R2?
No, it's actually going to be a minus there because, again, it's due to the notation that we have here. it does come out to be a negative sign here also. Okay, the only plus, the difference here is the plus is out here, and the minus is up there. Okay, and that arises because, again, this is squared in here, so it kind of takes care of that negative nature to it. So if you think about it a little bit more, it'll kind of be okay, I think. If not, we could talk about it some more. But yeah, I had the same concern, so I had to go through it before as well. Okay, so let's. So if we use this binomial expansion again, in this sense, the binomial expansion too is going to give us something in the paraxial regime, right? Because the x squared and y squared for the binomial to be true, right? This has to be less than 1. So again, we're talking about areas that are close to the optical axis, and so we can write again this square root of 1 minus x squared plus y squared over r1 squared. Using the first two terms of the binomial expansion, this will be equal to 1 minus x squared plus y squared over 2 r1 squared, and similarly the square root of 1 minus x squared plus y squared over r2 squared. This is equal to 1 minus x squared plus y squared over 2 r2 squared. Okay, so this will be good, because now we can think about how to use this a bit more, and so we can now write combine these, okay, in our total delta function, and we have now that this is equal to, so we combine this and this for these sections as well as that center section. So we have here that delta 0, again that includes that delta 2, which is that center constant slab, minus x squared plus y squared over 2 times 1 over r1 minus 1 over r2. All right. Okay, so that's good. All right, so this gives. So what is this? This is the thickness function. All right, and so the thickness is going to translate into a phase when we kind of multiply it by the index and multiply it again by 2 pi over lambda. So that's going to give us the phase of the transmittance function for the lens. All right, and so we can now write that transmittance function again for the lens as being equal to, we have this term out here, so that's just a constant. It's actually not going to be of too much consequence. J, K, N, delta 0. So you see here that we have 2 pi over lambda and delta, which is the thickness. All right, so that's good. And then we have, taking our further terms here, for the phase, converting it to the phase again. So now we have minus J, K, and we have N minus 1, right? Because we're taking these thickness values minus 1, right? If there's either index or air there, and so we need this N minus 1 term, and then this is times the x squared plus y squared over 2, and then times the 1 over r1 minus, 1 over r2. All right, so that is our transmittance function for the lens, and we can kind of simplify it if we notice that if we take this term here and this term. Do you recognize what that is? Okay. Well, that's the focal length for a simple lens, right? So 1 over f is equal to, or defined as, from this lens formula or whatever, n minus 1 times 1 over r1 minus 1 over r2. Probably those of you who took the prelims last week certainly will know that by now, or should have reviewed that at least. Anyway, if you haven't, that's the lens formula for the focal length. All right, so the advantage of that is now we can write this transmittance function for the lens more simply. So we have t sub L of xy, and again, so this is just a constant phase. All right, so constant phases are not very interesting and don't really have much consequence. It's the changing, the functional phase terms which are important. So we can now write this simply as the exponential of minus j k over 2f x squared plus y squared. So what does that look like? What does that function look like? How about like a quadratic phase, right? We have these square terms, right? So this is looking like a quadratic phase function, which is going to become very valuable in dealing with the Fourier transforms, because if you recall, in some of those we had quadratic phase functions. All right, so let's see what happens when we work with this. All right, so so now if we want to know what the field function, so what we really want to know is, so we illuminate this, say, if you took a lens here and you illuminated it, you know, what you end up with now past this lens is a quadratic phase function with this negative sign. So it's converging, all right? So as you might expect, it's converging to that focal point, right, given by that distance f. All right, so this is our field that we have now, say, just past the lens. All right. Again, if it's just that would be the case if we are using our normally incident plane wave condition, we end up with that u sub L prime. All right. So let's go back to our case 1, where now we're going to place that object transparency here in front. So we place that object there in front of the lens, and we're now going to see what happens in the back focus of that lens. All right. So one other thing we'll do too is we'll limit the size of the lens or the size of the transparency. So we can do that with a pupil function, p, or an aperture function. Let's not call it a pupil function since that has some other connotation. So we have an aperture function, which is just equal to 1 when it's inside, say, the aperture, and 0 when it's outside the aperture. All right, so very simple aperture function. All right, so now if we now want to know what this function is behind the lens here, we would have the function that is just prior to the lens, and then we multiply it by this pupil function and multiply it by the transmittance function for that lens. All right. So now this u sub L, say, with the t sub A, so we have u sub L prime of xy, so that's right here again. This is going to be equal to whatever the function is just prior. So we have a u sub L just prior to the lens. After the object transparency, so we have u sub L, again that's of xy, we have p of xy, and then we have exponential, this is the transmittance function of the lens, of minus jk over 2f x squared plus y squared. Okay. All right. So now, all right. So let's then propagate it out distance f and see what happens in the back focus out here. Okay. All right. So now the field in the back focus, u sub f, back here, let's give it coordinates u and v. That's going to be, and let's say that f satisfies the Fresnel propagation distance condition or requirement. It's far enough away so we get Fresnel diffraction occurring. So we have this u sub f of uv now is going to be equal to exponential of jk over 2f u squared plus v squared over j lambda f. So again, we're putting z equals f in our Fresnel relationship. And then we do the integral, the transform integral. And we're transforming, again, we have u sub L prime, which is, again, at the start of our Fresnel propagation distance. So we have u sub L prime of x, y. And then for Fresnel propagation, we need the quadratic phase factor. Right, exponential of j k over 2f x squared plus y squared. Right, and then we have the integration kernel here, exponential of minus j 2 pi over lambda f x u plus y v. And this is integrated over dx, dy, the sort of the starting coordinates out here at z equals 0. Okay, so this is, you might see that this is going to be pretty slick because now we're going to put, for u sub L prime, we're going to put this in there, right? And you can see right away, we have this quadratic phase factor is going to cancel that one, all right? And so what we're going to be left with now is that u sub f of u v is equal to exponential, again, so we still have this quadratic phase factor out front, exponential of j k over 2f u squared plus v squared, like so, over j lambda f. And then we have the integral minus infinity to infinity of u sub L of xy, which is, again, the function, the field function just past that object transparency, which is basically equal to the object transparency function, times that aperture function p of xy, and then exponential of minus j 2 pi over lambda f x u plus y v integrated over dx dy. All right, and again, so this with the normal incident plane wave is just equal to t sub a of xy with that condition, okay? All right, so this is now simply the Fourier transform of the transmittance function, the object function, and that's what we find on the back focus, except that we also have this quadratic phase function out front. So we have a curvature out here, right? I guess it's expanding, so it's still kind of going like that. And on top of that is this amplitude transmittance function, okay? Which is not always a problem. It's not always a problem if we're just interested in, say, the intensity of UV. In this case, we can get rid of that and end up just with the area squared over lambda f squared, and then we would have just the magnet or the transform squared here. So we end up with, again, minus infinity to infinity, t sub a of xy, exponential of minus j 2 pi over lambda f xu plus yv dx dy squared. So if we're just worried about the intensity, we're okay. But if we're doing holography, right, we're worried about what that phase function is at the hologram recording plane. So in those cases, we do need to worry about, say, this added phase function, because this is essentially going to look like a kind of like a lens function, right, or a negative lens, right? It's kind of an expanding lens at that focal plane. So we'd be recording that lens function plus the transform of the object that we actually want, which would end up giving us some kind of pseudoscopic effects. And you might have seen this in some early books on holography. You'll see that they talk about this pseudoscopic effect. So that's kind of what they're talking about. They do this recording, but they end up with, you know, these other phase functions that are encoded. And you know, if you record, say, with a spherical wave of some sort, you're going to see an image which kind of looks like it's imploding on itself or expanding, and that's where that originates. Okay, it could also be a problem if you're doing, say, optical data, holographic data storage, right? You may not want to have these different functions being encoded, because that would result in some strange magnification, which would be difficult to kind of deconvolve out of the, or to pull out of your data set after you do the recording. So there are consequences to having that function there. Of course, this was very easy, right? I mean, it's pretty easy to just put some sort of object function right up against the lens and work with it. But we can get rid of that function too. So that's what we'll look at next. All right. So for case 2. Case 1 was when we had the object transparency right up against the lens. So now what we're going to do is remove that from the lens at some distance. So we have, here's the lens that we have, and in front of that lens at some distance d, we are going to place the transparency. Okay, so this now is the object, which is our t sub a function that we have of xy, all right? And then what we're going to look at, again, is the diffraction pattern that we end up, that's formed in the back focus of this lens, all right? So, like so. All right, so this is the case we'll be looking at. So let's make a field. So we'll illuminate this with the normally incident plane wave. This will form a object field, say u sub 0, directly past that. And we could also have a spectrum of that object field. Right? We could take a Fourier transform of that, and we can get a spectrum of the object field as well, right at that location. And then, of course, what we'll do is we can allow this field then to, in order to get to the back focus, we have to allow this field to propagate to the lens, and then we have to apply the, the lens function that we have, or the lens transmittance function that we have, and then allow it to again propagate to the back focus. All right. So we can do this in a very straightforward manner with the integral relationships, but let's try a little bit different approach this time. Let's use some more finesse with the Fourier analysis. And so let's treat this particular problem by looking at the spectra of these different fields and see if we can come up with an answer, maybe a little more simplified manner of solving the problem as well. All right, so we have, again, the spectrum of the light transmitted by the object transparency, and so again, so that's going to give us some frequency spectrum, f sub 0 of fx and fy, where Again, so fx is like x over lambda z or d in this case, and similarly for fy. So those are, you know, that's a frequency representation of that object field. And we can also say that we have the field now is going to propagate out to here. So we would have a u sub L for that field, and we could also have a frequency spectrum for the field just prior to the lens. All right, so we have u sub L is the field after it propagates just prior to the lens. And similarly, we can have a frequency representation of that f sub L, again of f sub x and f sub y. And this is, both of these are just the Fourier transforms of these fields. So this is Fourier transform of u sub L, and that's the Fourier transform basically of maybe some amplitude times transmittance times t sub a, right? For that representation. Okay. All right. So now let's use some Fourier razzle dazzle here. All right, and see what we can come up with. Recall that we said that we can represent this diffraction effect as a convolution, right? So remember, we have u sub x of y. This is equal to the convolution integral of, again, u at the aperture plane, chi and eta here, times a kind of an impulse response, which is part of this convolution integral. So we have x minus chi, y minus eta, and this is integrated over d chi, d eta, all right? Where h now, h of xy is equal to e to the jkz over j lambda z exponential of jk over 2z x squared plus y squared, all right? And if we were to take the Fourier transform of this, right, we would end up with the product of these two Fourier transform functions, right? Or the transform. So what I'm trying to say here is that if we take the Fourier transform of u of xy, this is equal to, we'll represent the Fourier transform of u as this upside down u, like so, times the Fourier transform of that function, all right? So the Fourier transform of the impulse response, h of fx, fy, so that's the Fourier transform of this that we have out here, all right? So I'll just put that like so. And this is going to be equal to, you know, if we look up what the transform of that is, that's equal to e to the j kz times the exponential of minus j pi lambda z fx squared plus fy squared. Okay. All right. So this is kind of in general what we would have. So if we go back now to the case that we're looking for, so now what we want to have is what is the Fourier transform of the field just prior to the lens. So we can write that f sub L of fx, fy. This is equal to the product of those two functions, right? So one is of the two spectral functions. So one is f sub 0 of fx, fy, right, that we had up here. And the other is the h, all right? And so we'd have that times exponential of minus j pi lambda d, since the distance we're propagating over, again, assuming it's Fresnel region, is d times fx squared plus fy squared. All right? Okay, so this then is the spectra of the field just prior to that lens. All right? So now what we want to get is we want to get what the field is at the focal plane, right? And so now recall that if we want that, we take, what passes through here. So we have that u sub f of uv is equal to exponential of jk over 2f u squared plus v squared, like so, over j lambda f times the integral minus infinity to infinity of u sub L of xy. Again, we'll use that aperture function p of xy, 1 in the aperture, 0 outside, times the exponential of minus j 2 pi over lambda f xu plus yv dx dy. So what we're doing here, right, is we're just using the result that we had from last time, right? There we said that if we place an object right up against here, or if we have a field right up against there, this then is what happens in the back focal plane, right? So that's all we're doing here is we're applying that to this case, all right? And this is just equal to, again, I'm going to call that C, so I don't have to rewrite all that stuff. This is just equal to that, and this is just equal to the Fourier transform of that field prior to the lens, right? So this is u v over lambda f, like so, okay? All right, so we now have simply that u sub f in the back focal plane is equal to that, all right? And if we now write out what that Fourier transform is, we see we'll get the result, all right? So again, so this is our u sub f of uv now is going to be equal to the exponential of j k over 2f times, remember we have this is part of the field function here. We have this from this impulse response. So we have we get a d factor in this factor out in front. So this is j k over 2f 1 minus d over f times u squared plus v squared, okay, over j lambda f times the Fourier transform of the object field, u over lambda f, v over lambda f, all right? So, and then, again, so we can write that out a little further, and that's just going to be equal to the Fourier transform of the transmittance function, chi eta, exponential of minus j 2 pi over lambda f. I'm not going to have room there, so that's chi u plus eta v d chi d eta, like that. All right. So the important, and this is that. All right. So the important thing here is, notice that if we place the object a distance d equal to f out in front, right, then this term becomes 0, and that quadratic phase function that we had that was multiplied by the Fourier transform goes away. All right? So when D equals F, or in other words, we place the object in the front focal plane, then we get an exact Fourier transform of the object in the back focal plane. Okay, so finally we can get rid of having to go, very large distances by simply using a lens. And if we really need the exact Fourier transform, we can place that object out in front. And a 4F system is, so as you might expect, if we do a Fourier transform here, if we want to reconstruct the object, you want another 4F system. If you recall our inverse Fourier transform theorem, you want another Fourier transform to reconstruct that exact object. So that's why a 4F system is so widely used in optics, because you can take the Fourier transform and then unfold that Fourier transform and regenerate the object. So the nice thing, so what you can do in that case, when you get into the Fourier plane, you can start doing manipulation of the spatial frequencies. So for instance, if you want, like we have this problem now in one of my systems we're working on, we want to get rid of a lot of the background level in the system. So you can do that by putting an aperture or doing some phase contrast or some type of apodization and manipulation of the spatial frequencies inside that Fourier plane. So we design our system so we have access to the Fourier plane. We insert some sort of manipulative device there, which in optics is very simple. It could just be, your finger for all, or some little object, a razor blade or whatever, and you can cut out a bunch of light that you don't really need. When you reconstruct it, you can dramatically improve the contrast in your imagery that you're looking for. So, extremely valuable and very powerful tool that's used in optics all the time in a lot of different optical information processing. Okay, so I think we have all the Fourier tools that I wanted to give you. I know you cover this in great measure in some of your other classes, but at any rate, these are the tools that we'll be using in this class. So any questions on that? So, and this derivation, in case you found my derivation a little confusing, if you look in Goodman in chapter 5, he goes through it there, and that's where I took my pretty much summarized what he had done and reconstructed it for you. Okay.
Can you just go very broadly back over just the basic steps of what you did?
Okay. Yeah. So what I had done here is we set up the problem, and then what I had you do is to consider both the field and the spectrum of that field at these different locations. Yeah, so we have a plane wave, and then we end up generating the object field out here, all right? And then we propagate that object field or the spectrum. We can propagate either to the front of the lens, all right? And then, so we're assuming, in each case, we are assuming just Fresnel diffraction applies, both in this propagation and also here. All right. So then what we did at this point is said, okay, so we have a situation here where we now have the field in this just prior to the lens, and to get that, I used this relationship here, where we considered the Fresnel propagation as being this convolution integral, and so we have the product of F sub L and H, okay, just prior to that lens, which has this distance in it, D, okay. So this is, again, so this is going to be basically F sub L is going to be equal to F sub O times H with the D in it, with Z equals D. And that's what we have here.
This is to get the field before the lens.
Yeah, that's to get the field. See, that's what we have here, right? Okay, and then, so here's the tricky part, is I say, okay, we just went through this problem where we know what the field is just before that lens, and then let's see what happens in the back focal plane. And that result, the transfer function of the lens cancels that quadratic phase factor that was in the Fresnel integral. And so we end up with this for this second case, all right? But now we also had this term in there too, okay? So we had we have one factor, so we have this factor with the F in it, and we have this factor with the D in it, or the 1 over F and the D. And so when we combine those, we end up with this, okay? So again, I'm glad you brought that up. It's good to, because it is kind of, what did he really do there, kind of thing. But so we end up with, again, that transfer function giving us that D, and then from the lens transmittance function and taking that to the Fresnel propagation, we end up with 1 over F in this same factor. And so we basically factor out the U squared plus V squared, and we're left with this. All right. And so now, if we choose D equal to F, we then see that this whole front phase function drops out, and we're just left with the Fourier transform of the object function, which was, basically the Fourier transform of the transmittance function for a normally incident plane wave. Okay.
So where is the equation that shows us right after? Is this
I didn't do that. I didn't do that here because I already did that here.
So you basically did a Fraunhofer or a transform to go through the lens. So like an approximation.
Okay, so what did I do here? So what I did here was I said, okay, I take the field just prior to the lens, and then to get here, I have to propagate from just past the lens to the focal plane. So what happens when I go just past the lens? Well, I have my object function, which is here, and I have the transmittance function of the lens. Okay? That transmittance function of the lens canceled the quadratic phase factor in the Fresnel integral. All right? And so if I have a lens here and an object just in front of it, I end up with the Fourier transform of that object function, but I have also out in front this quadratic phase function. All right? So in this second situation, I incorporate this distance here. So I now move that object away from that. I do another Fresnel propagation, but I don't bother with calculating what happens here because I already know what's going to happen because I just did it in that prior case, you see. So that's, yeah, so you can do that, and you'll get the same result. We can just go through, I didn't plan it out in my lesson here, but you can actually just do it stepwise and solve the problem that way as well. And you'll find that you get exactly the same result, and that result is that you have sort of this multiplier in that phase factor that's out in front, and then by selecting D equal F, you can eliminate that secondary phase function. So now you don't have to worry about it. And again, so that's why the 4F system is very valuable because you get this exact Fourier transform of your object function in the back focal plane. Okay? Yeah, I'm glad you brought that up, because I know the first time I went through this too, I was, a little taken back about exactly what had happened there, but that's it. Okay. All right. So now, if there aren't any other questions, I'd like to look at another problem in using the Fourier analysis, but now let's apply it to a holographic problem. All right. And so we're going to look at an off-axis hologram, and we're going to analyze it with the Fourier analysis. To set the design condition for the hologram. All right. And so let's see what I'm talking about there. All right. So first of all, for the off-axis hologram geometry, we'll use this, where we have, here's our film or recording material, like so. We place an object transparency here. And remember, for the on-axis or the Gabor hologram, we illuminated that transparency straight through, like so. And we end up with part of that being scattered. So we're going to have some scattering by the object. So this is our T sub A, the object. So we'll have some scattering out here. That depends on the spatial frequencies of that transparency at those different locations. And we would have the residual amount of the light that wasn't scattered serving as the reference wave. Well, let's add to this. So we still have that, all right? But now we're going to add to it an off-axis reference beam that we're going to have come in at an angle of, we'll call it 2 theta. Here, this distance separating the film and the object transparency is z sub 0. Okay. All right. So we now make a recording of that composite, and now what we want to see is what is the kind of the Fourier spectral representation of this, and can we use that Fourier spectral representation to kind of come up with the design conditions here, mainly the biasing angle that we would need in order not to get overlap of, say, different spatial frequencies and get, that sort of aliasing that we saw when we have that inline hologram, where we have all of the fields reconstructed on the same axis. And then also, if you recall, in order to eliminate some contrast issues, we had to make a transparency which was actually a positive, which required us to do a copy of the negative, which you normally get when you do a photographic film recording. So let's see if we can eliminate some of those complexities with this and what the conditions are for us to do that. All right, so first off, the combined fields at the film plane that we have here. So here's our u again. So we have u of xy. This is going to be equal to the object wave. So we have a, we'll call that a of xy. Here, and that's going to be, again, part of this which propagates from a. And then we have the reference field, which is another amplitude, possibly a, times the exponential of an off-axis plane wave, e to the minus j 2 pi alpha x, where alpha is just equal to sine of 2 theta over the wavelength, like so. All right. All right, and the a, all right, the object field that we have, we'll call this as being equal to a amplitude function a of xy and a phase function, e to the minus j phi of xy as well. All right? So again, what we're going to want is, what we're going to record is the intensity I at the film plane, I of xy, and that's going to be equal to u star that we have there. And so that's now equal to a squared plus this object field squared plus a tilde of xy exponential of j alpha 2 pi x. And then we also have plus a times a star xy to conjugate exponential of minus j alpha 2 pi x. All right. Okay. So again, if we so that's what we have, and again we can. This is basically a classic interference pattern, right? So we can write this more suggestively for our purposes: a squared plus a squared, say of xy. We get rid of the complex there, and then we have plus 2 a. Again, that could be a function of xy, cosine of 2 pi alpha x minus phi of xy. All right. So again, what we see is this. We have this combination of the carrier. All right. So this is our reference or carrier frequency, plus the object frequency that we're trying to record. And so one way for, so you can start to think of this is that in order for you to not have these overlap, right, you need to design your carrier frequency in such a way so that it will allow these different frequencies in the object field to be unambiguous, all right? And this actually, so this off-axis hologram was invented by Leith and Upatniks, and they were working on radar systems at the time, so they were very familiar with, carrier frequencies and modulation functions and things of that sort. So, so this came out of that type of an analysis. All right. So, and that's the kind of analysis that we want to apply here to see how it can be useful for this purpose. All right. So, this is our intensity pattern. So the next step, of course, is to make the hologram. All right, and so we're going to have a transmittance function, say for of the film that we have here is going to be equal to some bias transmittance level plus a constant that is some gamma function, some linear response function times the say the exposure time times this intensity that we have here, I of xy. Okay? And so we could say maybe make that equal to a beta prime, for combining all that into, it's just a constant, just our exposure time and film response. And so now we have that this film transmittance function of xy is equal to, again, a kind of a bias transmittance plus the beta prime times a squared plus a times a e to the j 2 pi alpha x plus a times a star e to the minus j 2 pi alpha x. All right. And so we have 4 terms, right? So here, this is, we can call that T1. This will be T2, T3, and T4. There's 4 transmittance terms that we have for that particular hologram. All right, and so, if we then, so again, our next step is we make the hologram and then we reconstruct the hologram. All right, and so if we illuminate it with again, a normally incident plane wave, it could have some other amplitude, B or something like that, but we can basically end up with, we're going to end up with 4 field terms. U1, which is basically going to be equal to T sub B, U2, which is beta prime times A of xy squared, U3, which is this beta prime, this transfer constant, A tilde of xy, e to the, or exponential of j 2 pi alpha x, and U4, beta prime A star of xy, exponential of minus j 2 pi alpha x. All right? So these 4 terms, what do they correspond to? Well, again, this is just the kind of an attenuated 0 order beam, right? U2 is a kind of a spatially varying plane wave component, okay? And we have sort of this magnitude times its complex conjugate. U3, as you can see here, this is going to be proportional to the original object wave that we have here, and this to the conjugate object wave. Okay? And they are shifted, all right? They are shifted, as you can see here very explicitly, by this term, this single frequency, right? This is a single frequency term where, again, alpha that we have here is equal to sine of theta over lambda. So it's a single spatial frequency shifting the object wave and the conjugate by a negative value for that. All right? Okay.
Is it significant that earlier we defined alpha as the sine of 2 theta instead of the sine of theta?
Oh, I'm sorry. Yeah. I don't know. I again follow this from Goodman's. He liked to use 2 theta in there for some reason, and I'm not.
And it never changes from 2 theta?
Yeah, he never. I think I'm going to redo it and just put theta there because I don't. It doesn't really seem to drop out, or that factor of 2. So I don't really see a need for it. And by the way, the reconstruction that we're doing is a very specific reconstruction. All right. So instead of doing it in a normal way where we would say come in with this plane wave off axis, let's come in with the plane wave on axis. All right, so here we're going to have, we just come in with the plane wave. Here's the hologram, like so. And so these these different components are going to. So this is going to correspond to, say, U1 out here. And then we're going to get some, again, we're going to get some scatter in that. Notice here, this one is not shifted. So this is, this U2 is out at a little bit scattered around the 0 order that we have. And then we have the original object beam here is going to go off at an angle of 2 theta. So this is going to go, it's going to look something like this. Out here, and so if you were to observe that field, this is going to converge down to this is our A of x, y that we have. And this is going to be, of course, a virtual image. And it's located at a distance z sub 0 in the back here. And we also get another beam which is going in a negative 2 theta direction. So again, so this one here is 2 theta, and then we also have another field that propagates downward giving us the A star. Out here, again, that's also a distance z0 away from the hologram plane, and this is at minus 2 theta, corresponding to that. So again, it's a different reconstruction than we're used to, but I think it'll show some of these values a little bit better, or the Fourier characteristics a little bit better. Okay. All right. So now, if we look at the Fourier or the spatial frequency representation of these different terms, we have the following. All right. So we have, we'll call them the frequency spectra G. So we have G1 of fx, fy. This is equal to the Fourier transform of, say, T1 of xy. And remember, T1 was just a constant. All right, so this is just going to be equal to a delta function, right? So it's TB times a delta function of fx and fy. All right, and the other functions, I don't know if I'll have time to get through. Yeah, I guess I'll just write them all out. I'll have to, anyway. G sub 2 of fx, fy. This is equal to, again, Fourier transform of T2, and that's equal to beta prime. And we have this function times its complex conjugate. And so that's the autocorrelation, right? Remember that identity that we talked about before, or in that original set of Fourier transform operations. So this is the autocorrelation of G sub A with itself. Okay, where G sub A is the Fourier transform of A of x, y. Okay, I think maybe I'll stop there and I'll finish going through the rest of the terms and showing the significance of that next time. Thiago is here, and I think he has your homework assignments graded from homework 1. Yeah, there are a couple of labs here. I'm going to make the lab due officially on Thursday. I guess I didn't set a due date. So anyway. Okay, so we'll see you guys on Thursday. And again, so the midterm is going to be on October 22nd, which is a Thursday. Okay. All right. Good.
This is the 27th.
22nd.
Oh,
22nd, yeah.